First, let us celebrate a thing that the DEM excels in doing: treating mixtures of particles. This is something in between the lines, but becomes transparent when looking at this graph here from Chang and Zhao. Shown here is the relative volume, i.e. the total volume normalized with the particle volume for an array of binary mixtures of particles with a size ratio of 8:2. Clearly, in case of purely large and purely fine particles, this relative volume is the same, approximately 1.68 or so. In short, the absolute size of the particle does not matter as long as they are not cohesive. Of course, if the small particles become cohesive, their relative volume V will increase. But what is very interestingly, that the relative volume changes in a non-linear fashion between those 2 points A and B. Thus, it is essential to capture polydispersity, which is what the DEM can do without additional submodels, and this is really important. As you will see from the counting of particles, the number of small particles to be tracked is substantially larger than that of the large particles. As we have already heard at the beginning of this unit, this suggests to group particles to so-called parcels to reduce these computational entities to be tracked. You will see later how this can be achieved. Furthermore, the minimum to maximum particle diameter ratio matters, and hence you want to keep that close to unity. Chopping the particle size distribution is, consequently, a strategy to greatly reduce the computational effort associated with a DEM simulation. Another important aspect of the DEM is the analysis of data. What we do here is to move with the mouse cursor individual particles in a bed of sedimented particles and observe the effect on the packing as well as the resulting normal forces. We immediately see the formation of force chains in the network, which become even easier to identify once we activate more advanced post-processing. It is not visible when looking at the density, but when looking at a particle pressure that we will define in one of the upcoming chapters. Next, let us look at silo flow. Specifically, we explore the effect of friction in a silo filling application. As we can easily see, friction parameters between particles and between particles and the wall matter. Also, as you will see at the end, even with zero friction, there is a certain angle of repose. This is possible simply due to the geometry of the confining walls, the location of individual particles, and the way particles are filled into the silo. Another key example is shear flow, here with special boundary conditions at the top and the bottom. As you can see, initially we slowly shear in a clockwise direction. Left, we see a deep analysis of the orientation of contacts, normal forces and tangential forces. Important integral parameters are analyzed here at the bottom right in this left white panel. Next to anisotropy parameters, which we will highlight later, this is the macroscopic friction parameter shown here in red. As you will see, if we reverse shear, i.e. shear counterclockwise, anisotropy and macroscopic friction change rapidly. Look at that. The macroscopic friction approaches zero at the time instant we reverse the shear direction. As you can see, a very complex behavior can be produced even with spherical particles in a DEM simulation. Again, we will hear about details later, but what it is clear is that particle pressure and force chains also play a central role in such shear flows. Finally, we look at the uniaxial compression of a granular sample confined by lateral walls. As you will see, also here the behavior is highly nonlinear, and we observe a significant difference between loading and unloading, as well as multiple repetitions of identical loading cycles. Also here, force chains are visible. And the stress for the same vertical displacement also depends on the loading rate, meaning on the speed of compression. The time is ripe to conclude. We have learned that soft sphere DEM simulations are helpful in a plurality of multiphysics applications, ranging from simple granular mixing to the modeling of chemical reactors or battery research. The key message was that relatively simple particle scale models, e.g. for the contact force, are able to predict complex macroscopic behavior. This is also one ingredient for the great success of the method: predictive power. Still, the simple particle scale models require a plurality of input parameters. I hope I have given you a taste what these parameters are and how they should be chosen. We have already touched on the importance of using parcels for computational reasons and the challenges that arise with polydispersity. We will definitely come back to these topics in the upcoming units. Finally, researchers cannot see without eyes, meaning we need excellent post-processing to gain knowledge from the zoo of data that DEM can create. As you will see, this is like finding the needle in the haystack. Distill a single meaningful parameter from millions of data points you get from a DEM simulation. All this feels like no pain, no gain. And this is indeed true. So let us round up this unit with some experts that comment on the gain for science when using the discrete element method.
Hello, I'm Peter. I'm a senior scientist at RCP, the Research Center for Pharmaceutical Engineering in Graz. I work on understanding the basic behavior of flowing powders when applied to pharmaceutical manufacturing processes. Powders are funky because sometimes they are like fluids, sometimes they're not. In this particular case, the particular particles have a property known as dilatancy because powders, individual grains cannot be compressed beyond a point. If you want to shear material, these individual particles have to push each other out of the way. This creates this low density region in regions of shear, also known as dilatancy, a cool phenomena found by Reynolds of Reynolds number fame over 100 years ago. For powders, we found the presence of secondary flows even at very low inertial numbers, and that is a really cool concept that DEM helped us find.
Hello, my name is Simon and I'm from the Johannes Kepler University Linz, and my research interest is the numerical modeling of turbulent industrial scale gas particle flows. This is particularly important for steel industry and its transition to carbon-free steel production.
So when set up as a bonded particle model, the belt is able to react dynamically and locally to loads from the bulk material on the belt, as well as to components keeping the belt in place, such as idlers and pulleys. An example of a belt conveyor system where this can be visualized is a sandwich conveyor, where the deformability of the belt is of significant importance. This system transports the material with it clamped between two belts.
Thank you, Peter, Simon and Eric, for your expertise that you contributed to this MOOC. I think we are done now for this unit and can start soon with the next one.